Hi class, this video is on topic C6, Millikan's oil drop experiment. So today we're going to talk about a very famous experiment from the early 1900s called the oil drop experiment. It's really important to understand how this works and how this was set up because it brings together many concepts of this chapter. So Millikan had the question, is there a smallest unit of charge that nature will allow? And he predicted that the answer was yes. And his series of experiments proved that the answer is yes. And he also determined what the smallest charge is. It's the charge of one electron or one proton. So it's an important experiment to study. So let's just recap some things in previous lessons that will be important for deriving our equation for associated with Millikan's oil drop experiment. So recall that if you have two plates with equal and opposite charge, an electric field is created that is uniform. So anywhere in this field, there is a constant electric field strength of epsilon, and the direction is positive from the positive plate to the negative plate. And that's the direction that a positive charge will want to go. This means that a charged object would experience a constant force. So recall this electric force equation, that the direction of epsilon is a vector and force is a vector, and the directions exactly match from the positive plate down to the negative plate. And if epsilon is constant for then a given charge, force is constant. So the force is constant anywhere between these two plates. And then in this uniform electric field, that force is calculated using this equation. And if we take a positive point charge and place it near the positive plate, when we let go, the positive charge will want to travel to the negative plate. If we were to take an electron, put it in the middle here, it would want to travel in the opposite direction as epsilon. It would actually want to travel up to the positive plate. And we're going to be placing charged oil drops in between a parallel plate in a uniform electric field. So we also talked about combining the equation for potential difference with the equation for the change in electric potential energy, negative QED. And then if we combine those together, so we substitute negative QED, negative Q epsilon delta D into this spot here, we actually get delta V equals negative epsilon delta D. So potential difference equals negative electric field strength times displacement, or you can rearrange that for epsilon, electric field strength equals negative potential difference divided by displacement. Okay, so Millikan asked the question, is there a smallest unit of charge that nature will allow? And if so, what is the value of this charge? And it is predicted that this smallest charge does exist, and the value of the charge is an electron. And so this is the overview of his experiment, or of his, I guess, setup. So he had like an oil spray at the top in this closed apparatus. And in the bottom half, he has the charged parallel plates, which produces a uniform electric field in one direction. And the oil droplets will be charged on their way down, and there will be an electric force and a gravitational force. There's also a microscope. And the way that these charged plates, he accomplished the different charges is through attaching to a variable voltage power supply. And he would dial up or down the voltage. So the significance of his work is that This oil drop experiment demonstrated the elementary charge, or the magnitude of the electric charge carried by a proton or electron, which is 1.602 times 10 to the minus 19 coulombs, which is considered a fundamental physical constant. And it is impressive not only that he proved the answer to his question, that he got this number, and he got it quite accurately. So the number that he got from his experiments was quite accurate compared to a more precise number that we have today. The charge on any object, so another way of saying this, that there is a smallest unit of charge allowed in nature, is that the charge on any object is a whole number multiple of the elementary charge. So that's why we have this basic equation you might remember from grade 9, that the charge on an object is equal to the charge on one electron times the number of those electrons. And this is all where it comes from. So another way of saying it is that it's quantized. So the charge on an object, out of the possible charges, we'll look at some sample numbers in a few slides. So the purpose of Millikan's experiment was to answer that question using a constant electric field within parallel plates. And then the outcome of the experiment was that he determined what that smallest charge was, and is called the elementary charge, or E. Okay, so taking a close look at the apparatus and the procedure. So in step 1, there was a spray bottle that released oil droplets, and the oil droplets were charged by friction, so positively or negatively charged. And then some of those oil droplets fell through a hole that was one of the top plate. Let's say that the oil droplets ended up being a negative charge, and the top plate would be positive, the bottom plate will be negative. And the second step is due to their mass and gravity, the oil droplets fell into this hole. And then the third step, the charge of the plates was changed until one of the droplets was at equilibrium. And then at equilibrium, Fe equals Fg, and there is a calculation that we're going to do at this point to find Q. So Millikan adjusted the potential difference so that the drop was hovering. So any object with mass will accelerate downwards due to the force of gravity if there was no other force acting on it. But Millikan applied a voltage so that there was an upwards electric force. And if the oil, and we can calculate that force based on its, if this force, if we can know this force and we can know epsilon, then we can calculate Q. So we're going to do that in directly. So at a certain point, so this is a symbol for a variable voltage power supply. So you can dial up the voltage or dial it down, and he would do that to find the sweet spot so that the oil droplet would hover. So the FBD of this is Fe equals Fg. And then recall that the electric force on a charge in an electric field is Q epsilon. So we can sub that in for Fe, and then we can sub in Fg equals Mg. And then we can rearrange for Q. And then further, epsilon is equal to the potential difference across plates divided by the distance between the two plates. So recall that potential difference, it's the change in potential from one point to another. So if we select that to be here compared to here, then the delta D that goes along with that would be the plate separation. So if we take that equation for epsilon and we substitute that into the denominator, we get an equation for charge of the oil droplet, which is mass of the oil droplet times gravitational constant times the plate separation, divided by the potential difference that allows for this balance to occur. And the right side of this is all things that could be measured or known. So he was able to determine the mass of the droplet using the density and the radius. And then the density is mass over volume. This is small g, so 9.81 meters per second squared. Plate separation is based on his setup, so he could measure it or set it up to be a specific value. And then potential difference is based on whatever the dial says here, so that the balance will occur. So if we look at some results, different drops had different charges, but after a while he realized that all of the charges were a natural number multiple of some small constant charge. So if you take a look at this, if one electron is 1.6 times 10 to the minus 19 coulombs, the possibilities are 2 times that, 3 times that, 4 times that, 5 times that, or the negative versions of it. So the results showed this quantization of charge. And I mentioned before, we use a variable voltage power supply. We can dial up or dial down the voltage, and the 2 parallel plates allow the control of epsilon, and thus the electric force. And we can use this to balance the force of gravity. So there is a simulation that kind of helps visualize this. So you can see based on this voltage, we can have these oil droplets hover, which is the place where F net equals 0. And there's also another link that I'm going to, or another simulation that I'm going to link through to at the end of this video. So we're just going to go to it. So it says, click on the spritzer of the oil bottle to spray droplets into the chamber. So we spray some oil. And then it says, the drops will acquire a negative charge when leaving the nozzle on the bottle. Notice how some drops move up to the top plate and some accelerate downwards. So when we did that, so maybe the drops that accelerate upwards, they're so negatively charged that they travel up. And the ones that fell, they weren't very charged, or they weren't charged at all, so gravity took over. But for this one droplet here, well, it would be more than one droplet, but this one droplet in the simulation, if a drop does remain suspended, so looking at this, we have a certain plate separation, which was measured, and we have a certain potential difference, which is the V balance. In the equation, the B stands for balance, so it's the point of balance. It says click on the scope, the microscope, and now we're viewing the drop that is in equilibrium. So this is the oil droplet that is hovered there. We can measure the radius using what we see in this microscope. We know the oil density, since we know exactly what type of oil we're using, and then calculate the volume and mass of the droplet, and then we can do our calculation. Then we'll have the mass of the droplet, and we set QE equal to mg and rearranged for Q. So in that simulation, through the microscope and density, we found mass, had constant. This was plate separation. And this was the voltage that allowed that balance, that hovering to occur. So let's try an example. Millikan's oil drop experiment was set up, and two horizontal plates maintained at a potential difference of 360 volts are separated by 2.5 centimeters. A latex sphere with a mass of 1.41 times 10 to the minus 15 kilograms hovers between the plates, the upper plate, which is positive. Is the sphere negatively or positively charged? Calculate the magnitude of the charge on the latex sphere and determine the number of excess or deficit particles. Okay, so drawing a diagram first. So it's really important that you draw a diagram, or else you won't be able to communicate, I guess, your thoughts for A. So is the sphere negatively or positively charged? Well, it says the top plate is positive, the bottom plate is negative. Then we draw our sphere, and you know gravity has to be down towards the center of the earth, as it always is. The only way that there is an upwards electric force is if this droplet is attracted to the positive side. So we know the sphere is negatively charged, and we calculate the magnitude of the charge by saying, using the FBD to say Fg equals Fe, mg equals Q epsilon, mg equals Q times delta V over delta D, and then we substitute in our numbers. Remembering that whenever we use an FBD and we write some sort of dynamic statement based on FNet, we've already considered the direction based on the FBD. So we did Fe minus Fg equals 0, or the other way around. So this is just giving us the magnitude of the charge, but we still have to use the diagram and common sense to figure out if it's positive or negative. So this is negative 9.6 times 10 to the minus 19 coulombs. And then it says determine the number of excess or deficit particles on the sphere. We know that Q equals the number of electrons times the charge on one electron. So we can rearrange for N and see that this value is equal to 6 electrons excess. Okay, so now you have some practice questions to do. I recommend reading over the section in the textbook about this, and there's also recommended links to further explain the experiment in the same detail, but maybe different wording. So please make sure to submit the exit ticket associated with this video, and please do the practice questions and submit to Google Classroom. Have a great day.